Hello, this is John Cottrell from Matrix Science, and I'd like to talk to you about some improvements we made in the reporting of error-tolerant search results. An error-tolerant search is the most efficient way to find unsuspected modifications, non-specific cleavage products, and sequence variants. It's a two-pass search. In the first pass, we perform a standard search of the selected databases. We then select only those database entries that contain one or more significant peptide matches. This gives us a much smaller database, so we can afford a much broader search in the second pass when we search with relaxed enzyme specificity, a comprehensive list of chemical and post-translational modifications, and we allow for a protein database single residue substitutions, or if it's a nucleic acid database, we allow single nucleotide substitutions, insertions and deletions. Of course, there is nothing new about what I've just described. Error-tolerant searching has been part of Mascot Server for many years. The big difference in Mascot Server 2.8 is that we now use target decoy to assign significance to all the matches, including those found in the second pass search. As in previous releases, all you need to do to perform an error-tolerant search is to check a box on the search form. In Mascot Server 2.8, you can, and indeed should, also check the box to use target decoy. Without a decoy, expect values are derived from counting trials. That is, counting the number of candidate peptides that we test to try and get a batch. This estimate is not always going to be super accurate, particularly when there is something wrong with the choice of database or with the search parameters, which means that a large fraction of potential matches are unavailable. Ticking the checkbox to search a decoy database gives us a solid empirical basis for our statistics. There is also a new control on the search form to specify the required false discovery rate. The reason we ask for this up front is that the FDR determines the set of proteins selective for the second pass search. For example, the first pass search might identify significant peptide matches to 500 proteins at an FDR of 5%, and these are what go through to the second pass. If the FDR was reduced to 1%, the number of proteins selected for the second pass might drop to 400, so we would get slightly different search results. So although the FDR can be tweaked at the reporting stage, this will not give identical results to setting the required FDR up front in the search form. When the results come back, you have a single report that combines the results from both passes. The required false discovery rate is applied independently to the results from the first and second pass searches. But since this is based on counts of peptide sequence matches, it also holds true for the combined results. So if the first pass is 1% FDR and the second pass is 1% FDR, then the combined results will also be 1% FDR. Expect values are reported for both the first and second pass matches. In earlier versions of Mascot, an error-tolerant search could not be combined with target decoy, and expect values were only reported for the first pass matches, and they were based on counting trials. The way this all works is that target and decoy proteins are always treated as pairs. So after the first pass search, when proteins are selected, Each significant match, whether it's from the target database or the decoy databases, causes the relevant pair of target and decoy proteins to be selected for the second pass. This means that the target and decoy databases are of identical size and they contain all the significant peptide matches from the first pass. If a query gets a significant match in the first pass search, this is what we report, and we blindly discard the second pass results for this query. Now sometimes this may mean a stronger match is missed, but to do otherwise would be statistically dishonest. For example, if the significance threshold for a particular query in the first pass search corresponded to a score of 40 and we got a match with a score of say 52, this would be considered significant and this is what we report, even if the second pass search might have given us an even stronger match. Now, in some ways this is not ideal, but the alternative is to burden all matches with statistics based on both passes. To illustrate why this would be a problem, imagine that we were to look at the second pass results and actually find no better match. However, because we've looked at the second pass results, we now have a much larger search space and maybe the score threshold increases to 55, so that we now have to discard our first pass match with a score of only 52 because now it's no longer significant. Usually the search space for the second pass search is larger than for the first pass. This means that the significance threshold is more stringent for second pass matches. Here, for example, query 16581 gets a score of 85 in the first pass search, which corresponds to an expect value of 4.7 times 10 to the minus 9. Query 16432 gets the same score in the second pass search, but the expect value is only 1.2 times 10 to the minus 6, worse by a factor of 250. Finally, a few tips. The Unimod database contains a large number of entries that you do not expect to find in a general search. You can reduce the search time by excluding isotopic labels and also very large modifications which rarely give strong matches. I find 1 kilodalton is a good cutoff on the mass. Typically this will reduce the number of modifications you have to work through by about a third. Remember that the second pass search works through the list of modifications serially. It doesn't look for combinations of unsuspected modifications on a single peptide. So if you have a very abundant modification affecting 10% or more of the peptides, it's a good idea to specify this as a variable mod so that you can find matches to peptides with both this abundant modification and also an additional unsuspected one. The data used for the screenshots in this presentation was a search of LTQ Orbitrap Velos data acquired by the Medical University of Graz and deposited in PRIDE project PXD 002726. Looking here at the list of modification counts in the search results, you can see there's quite a bit of non-specific cleavage. N-terminal carbamidomethyl was also very common, so this was actually specified as a variable modification. The next most common mod is deamidation of asparagine, but since this only affects 3% of the peptides, it's really not worth specifying this as a variable modification. Even when the false discovery rate for peptide sequence matches is well controlled, the FDR for proteins will often be high for an error-tolerant search because we're searching just a few entries in the second pass. In our example search, at 1% false discovery rate for peptides, the protein FDR is 23%, which sounds just awful. This is simply because the 42 significant decoy matches to peptides are scattered randomly across 20 decoy proteins. If we increase the minimum number of significant unique sequences setting from 1 to 2 and choose format, we eliminate the one-hit wonders, and the protein FDR drops to a rather more satisfactory 0%. We don't get any decoy proteins in our results list.